Here's a really tough question that has confounded economists, academics, energy companies, and politicians for decades. How do we create more energy this year than we did last? That's cost efficient, geopolitically agnostic, and not so carbon dense that it further snowballs us towards environmental catastrophe. And furthermore, how do we produce that energy today in response to a world of increasing demand from data centers, EVs, batteries across the board, and the ballooning populations from developing countries consuming more and demanding a higher standard of living on the scale of 1 billion plus people? How do we do all this? While oil, gas, solar, and wind aren't going anywhere and are as important as ever, Quaise have frisbeed their hat into the ring with their own solution in tow. That solution being deep geothermal. And the case for deep geothermal is actually a rather simple one on the surface. There is an abundance of heat beneath our feet, always. Anywhere between a few meters all the way down to 20 kilometers beneath the ground you walk, right now, is hot rock, up to 300-400 Celsius. And that heat is always there. It has always been there, emanating from our planet's core since the second Earth was formed billions of years ago and will continue to do so for billions more. So the deep geothermal case is a rather straightforward one. Drill deep wells, boil water at those depths, and use the steam to generate a turbine that adds electrons to the grid. It's actually such a rich proposition, and as you'll see in today's interview, it looks like it's only an engineering problem in the way of getting there. Geothermal doesn't have the baggage weighing down its competitors. Oil and gas, while principally responsible for the level of civilization we have today, are equally responsible for our changing climate. Nuclear has the perennial problem of its geopolitically significant byproduct and all the bad PR from Chernobyl and all the rest. And then even solar and wind, you don't need to look far to see that even they, at times, get a bad rap. But deep geothermal is, so far at least, without these plaguing caveats. It may well be the cleanest, most discreet, powerful energy at our disposal. The question is, however, do we have the tech to enable it? The core problem is digging to depths where the rock is so hot that our traditional drilling technologies just can't do it without the economics completely falling apart. Matt actually gives a really good example in this interview of an 11-kilometer well recently dug in China that took 50% of the time, this is more or less, not exactly, 50% of the time getting to 10 kilometers and then 50% of that additional time just getting 1 kilometer more. So therefore it gets much more expensive, much more slow, and much more difficult the deeper you go. And the critically hot rock is 10 kilometers plus below the surface of the Earth in any given place. And if the critically hot rock is that 15 or 20 kilometers at depth, then we need to innovate a better way to dig down whereby the economics come up green rather than red. It kind of is principally the entire question here, which Matt really elucidates well in this interview. And that's where Quaise and Matt Houde enter the discussion. Quaise are a sci-fi company in all the best ways. They do not cut away rock with a drill bit. They instead zap away rock with a gyrotron a little bit at a time, thereby avoiding the costly and time-consuming process of churning through hard rock and replacing loads and loads of expensive drill bits. I'm not sure if Quaise would like this comparison, but if any of you have seen The Core, which was an old movie from the early 2000s, that machine they use is kind of the same idea. However, while this sounds sci-fi, this isn't some purely theoretical idea that falls to bits as soon as it's exposed to the real world. Just last week, Quaise, of which Matt is a co-founder, successfully applied this technology to a depth of 100 meters at a real-world site in Texas. And although it's not 20 kilometers, but just think about how long 100 meters is, this is an astounding achievement and proves that the technology is applicable in the real world, thereby creating a tremendous amount of excitement, optimism, and in my case, just raw bullishness that Quaise may well go on to prove their thesis. That with this technology, you can go, for all intents and purposes, anywhere in the world, drill a hole deep enough, attach some discrete infrastructure to the surface, and add electrons at scale to the grid. This is huge for the energy transition, but as well consequential, potentially, geopolitically. China import 20% of their gargantuan energy needs. They aren't blessed with the carbon density riches of the US, which allow their energy independence, but included in the promise of Quaise is a conceivable path to a type of energy independence that whether you're New Zealand, Vietnam, Finland, or Madagascar, or even the east coast of the USA, Quaise would be able to secure substantial and additional energy for these locations without the long supply chain once the well is in operation. And just compare deep geothermal to solar or wind. Solar needs to be where land is cheap and the sun always shines. With wind, the same economic and environmental dynamics. Deep geothermal requires a fraction of the surface area and the heat is always there. Matt Houde is the co-founder of Quaise. This is his second appearance on the podcast. And if geothermal is intriguing to you, then I would direct you to the podcast description where I put together a list of all the geothermal interviews I've done over the last few years. They include executives of ESG geothermal companies and as well various operators from several different angles of the geothermal industry. In this interview today, we discussed the success of the 100 mil drill in Texas, the big plans for what's next for Quaise, the business model of Quaise, serendipity and innovation at Quaise, and then plenty more in between. So therefore, finally, forgive the longer than usual introduction, but with no further ado, here is Matt Houde. Mr. Houde, thank you so much for joining me again.
Thank you for having me. It's good to see you, Ryan.
Yes, and so yesterday on your website, the press release was published. So Quaise has some pretty exciting news.
Extremely exciting. I think when we last spoke, we had drilled about 9 feet in the lab, about a 1-inch sized hole. We've 10x'd both the depth at which we've drilled as well as the size of the hole we're drilling. So our most recent milestone is actually drilling out in a true field environment, drilling a 100-meter plus deep borehole, about 4 inches in diameter, using a system that's able to generate about 10 times as much microwave output power as what we used in our prior lab testing.
Oh, wow. So not only have you sort of proven it at a not 10 kilometers, but a more shallow 100 meters in the field, but as well the gyrotron has become more efficient, 10x more powerful.
That's right. In summary, we continually need to increase the output microwave power through which we're drilling so that we not only increase the size of the hole that we're drilling, geothermal boreholes and wells are much larger even than traditional oil and gas wells and are typically at minimum 7 to 8 inches in diameter. So we need to increase the power with which we drill to increase that hole size, but also to hit our rate of penetration target, which I think I know that last time we spoke is around 3 to 5 meters per hour. That's a target we want to hit continuously with drilling and includes the time that we're not spending, quote unquote, drilling or rotating on bit. So we're addressing this increasing non-productive time that becomes an issue for conventional drilling as you go deeper and hotter with that rate of penetration target.
Totally. And that rate of penetration, that all just comes back to sort of the unit economics of any particular well, right? The higher your rate of penetration, the less labor is spent on all the people there and the rig and so forth. And it's literally just comes down to how fast can you be going down.
That's right. And drilling, time is money. So if you can drill to the same depth faster, you're saving money in the long run.
So this is from Carlos's statement, rather an excerpt from it. We drilled perfectly clean holes through some of the hardest rocks on Earth in record time. So I just wanted you to quantify both hardest rock and record time. Did you specifically go to a place that had particularly difficult rock, or rather is that just a sort of flagrant way of referring to any rock beneath the surface of the Earth?
So we are, with this demonstration, as well as where we want to drill with millimeter wave drilling in the future, we're drilling in hard crystalline basement rock that's representative of the rock you see pretty much everywhere on Earth once you get to a certain depth. So if you look at traditional drilling in oil and gas, almost all of the geology that they're going to be drilling through is sedimentary rock, sandstones, shales, limestones. These are rocks that are less competent than, say, a granite type rock that is more representative of the geology that you see at the depth and temperatures to which we want to drill. And so for a first field trial, we found a site located in central Texas where we were able to access granite very close to the surface. It's actually a granite quarry about a mile west of Austin in a town called Marble Falls. This site provides a lot of value in that we don't have to drill 2 to 3 kilometers to get into this basement rock to
Hmm.
prove out the millimeter wave drilling in the environment it's intended to prove its value. And so we're able to perform these shallow tests in this granite basement rock near the surface for proving out the next depth milestone that we've recently reached with millimeter wave drilling. And in terms of the rock strength, I don't have a number to quote you on that off the top of my head, but we know it's a very competent rock. We had a core driller that came out to the site about a little over a year ago to extract some core for us to better understand how the granite may change with depth. And their feedback was it's the hardest rock they had drilled in their experience.
Well, that's fantastic. I mean, that must be even more fulfilling because if the Quaise technology ends up being what enables ubiquitousness of geothermal, a huge part of that trade off is it has to be more cost effective than whatever traditional um, oil and gas drilling might look like. And especially because one of the big promises of Quaise is that it is ubiquitous across the world. You can really just dig anywhere because at a varying levels of depth, there's going to be the critically hot rock that's going to be able to produce electricity on the other end of it. So you did side by side it with whatever traditional drill bits can do, and then Quaise was way faster.
That's right. I wouldn't call it an apples to apples comparison per se. I mean, certainly core drilling is much different than the style of drilling you would use for simply drilling as fast as you can to get to your depth target, whether that's hydrocarbons or heat at depth, like what we're targeting. But it definitely was good feedback to know that this is a very competent hard rock to drill with mechanical means, and our millimeter wave drilling trial was successful and, in fact, exceeded the performance that we'd observed in the lab thus far, trying to drill similar rocks in a lab-based setting.
Does the rock get harder the further down you go, or is this pretty much as hard as it gets?
Typically, yes, but it's like everything in geology, it's hard to say on average the trend is going to be in this direction. I think certainly an easy way to conceptualize it is that most locations in the world, if you start drilling underground, right near the surface, you're going to have very unconsolidated subsurface, more or less soil and weathered rock. You then start to enter into more competent, what is often called bedrock, but is traditionally sedimentary formations that is competent rock, but not necessarily the hard crystalline rock where high temperatures are going to be found in most places in the world. And at a certain depth, you're going to enter into basement rock, where now rock is pretty uniformly hard and crystalline, tends to get mechanically stronger with depth. But of course, like everything in geology, there are surprises to be found as you go deeper.
Yeah, do you have any sense for what the surprises might be, or it just has to be wait till you find out?
I think we can expect that rock will be some form of a basement lithology. I think the most likely geology we're going to find drilling is going to be a metamorphosed derivative of a granite parent rock. So this was a granitic or igneous rock that over time has been exposed to pressures and temperatures that altered the original mineralogy of that rock type. Um, but certainly as we go deeper, we expect, additional challenges to be found as we continue drilling, such as drilling through larger faults and fractures,
Hmm.
drilling rock that is more heterogeneous than what we drilled in our field trial. This was a granite formation that I think is pretty consistent as you go deeper, but
Hmm.
we'll find certainly in our future drilling campaigns going deeper that you may not only enter different types of basement rock as you go deeper, but you may find certain seams of rock that is much different than the host rock.
Hmm.
To give an example, something that we see at this site in a limited frequency is a pegmatite type feature, which is essentially a thin seam within the granite where the mineralogy changes from sort of the standard base case composition of minerals we see in this granite into a composition that is more uniformly a potassium feldspar mineralogy or a quartz mineralogy. And that's the sort of thing that as we continue our field demonstrations, we want to understand how that affects our drilling process and how we optimize our inputs at the surface to drill through these inflection points in the host mineralogy such that we are able to drill at this steady rate of
Hmm.
penetration we're targeting.
And is the biggest risks as you go deeper where the water goes into the borehole, whether it collapses, or just the unforeseen maybe mix of rock that at each additional 30 centimeters of depth you might be encountering?
I think it's all of the above. I think definitely the way I like to frame our risks for drilling is, can we get power down into the hole? Can we get the stuff, the rock, out of the hole? And can we keep the hole open? And so, to your point, as we drill through various rock types, we need to understand the relationship between the inputs we control at the surface and the type of geology we're drilling, how we may want to vary those inputs for going between, say, a granite-rich zone into a
Mm.
rock that is more mafic or like basalt and vice versa. As we go deeper, we need to ensure we can get all of these cuttings out of our hole with the purge gas we're injecting,
Yeah.
given the fact that we aren't using the more traditional drilling muds that are used for this function. And finally, as we go deeper, I think that borehole collapse risk becomes a greater and greater challenge. We need to ensure this hole stays open through the lifetime of the drilling campaign,
Right.
such that when we want to install our long-term wellbore completion, which is traditionally steel casing plus a cement layer outside of the casing to keep the wellbore open, we need to
Hmm.
ensure that hole stays open until that point we can install the long-term wellbore completion equipment.
And I will explain in the introduction to the video, in very layman's terms, sort of what the technology is and what it is doing and why geothermal matters and all the rest, just in case, someone sees an episode of a guy from geothermal and decide I have no idea what that means or why that would be interesting to me. So you don't have to necessarily explain the technology in full, especially since you already did that last time.
Mhm.
But a really interesting detail that I saw from the real engineering video that was made on you guys, that might be the wrong name of the channel, but it creates this obsidian layer as it goes down, which is like this perfect byproduct that creates a wall for the hole, right? And that must be unique to the gyrotron technology, which other geothermal applications won't have. And therefore, presumably, that creates a more stable well.
That's certainly a possibility. I think in our current testing, we're more or less removing all of the components of the rock that we're drilling through, which includes the melt, something I think a bit different than the videos we've shown of some of our more recent lab testing. But a point of future exploration as we go deeper and need to address this challenge of borehole collapse is how we can sort of form a borehole that's able to remain open and is more mechanically competent than relying on the strength of the basement rock that we're drilling in. We do have, to our benefit, the fact that we are drilling in this very competent basement rock. These boreholes are able to withstand the stresses they're subjected to simply being reliant on the mechanical properties of the parent rock. But there's definitely going to be a depth horizon we reach at some point whereby this hole that has no drilling muds inside, it only has a purge gas as the drilling fluid providing additional pressure on the other side of the walls of this borehole. There will be a need to find ways in which we can stabilize that borehole for the lifetime of the drilling. And this melt layer that we can be potentially creating is a pretty exciting opportunity, in my opinion, for producing materials in situ that allow you to stabilize that borehole for drilling.
It's funny as you explain it, the the risk from a financial perspective starts to make a whole lot more sense, because if you were someone who was thinking of investing in Quaise, it's actually not as simple as just look at the temperature at this depth. We've got a technology that can drill the hole. It's a sure thing. It sounds like there is so many open questions and especially complexities that you haven't had to grapple with yet that might still, dampen the party for the promise of Quaise and deep geothermal.
I think there's certainly a host of engineering challenges we have to solve with the technology and the drilling process to address those risks that I mentioned. What
Mm.
gives us, again, confidence that we have solutions to address those challenges is that these are not fundamental physics-based challenges. We think
Right,
the
right.
physics of the drilling is fairly sound. We think, we know the rock, we have a good estimation of what kind of rocks we're going to drill, and for that reason, we have an estimation of how effective the drilling process is going to be in this deep basement rock. And we think with some ingenuity and research and development over the next few years, we're going to address those challenges head on and find ways to continue to scale the depth which we
Mm.
drill, which is important because at each extra kilometer we can go deeper. That opens a much wider market at which we can develop this super hot geothermal resource beyond the locations we could access those temperatures today with conventional drilling.
And what are you most worried about?
I think, definitely hull collapse is a technical challenge, and I think that's a little bit of my personal bias because I come from a geological engineering background, and so for me, the challenges related to the geomechanics in this hull are what I find to be some of the most interesting problems. I would say another challenge that is certainly something to address in the next 3 to 5 years is the supply chain for all of this equipment.
Mm.
This is a supply chain built for nuclear fusion research, not necessarily the most standardized, commoditized industry out there. These systems are usually built for one-off
One of a
science
kind.
experiments.
Yeah.
That's right. It's almost always one-of-a-kind units. And so in foreseeable future, we know the gyrotrons and waveguides can be manufactured today, can meet the specifications we need to mature the drilling and execute our first commercial field trials, drilling full-size geothermal holes. But if we can imagine a future 5 to 10 years down the road where we have tens, if not hundreds of these drilling rigs in operation,
Mm.
we
You're
have
going
to
to need so
address
many
that.
gyrotrons. Yeah.
We need to address that supply chain concern. That's right.
Yeah, that was a question I was going to have for you a little bit later when we got more into the business model of Quaise, because assuming that this project you do in 2028 works, it's like balloons everywhere. This is the best party of all time. I can't believe we managed to do it. What happens when, for instance, in Australia, all of a sudden there is demand for this technology? I think I read online the gyrotron alone costs something like 17 million USD, plus all the gases, plus the giant power generator behind it. These are all these one of a kind things that have to be shipped around on trucks throughout America. Like how much would the delay and the lag, and therefore that additional risk to exporting this project internationally, would that become?
It's definitely a risk for scaling the technology. I think it's not just the fact that the supply chain is limited in the quantity of units, the cost and lead time it can produce that quantity of units we would need for scaling. But there's also concern because these devices fall under a lot of export control regulations that
Mm.
can make it somewhat challenging at this point in time for being able to utilize this equipment and export it out into the world.
Mm.
Although it helps, being in certain countries rather than others, given just geopolitics and the relationships between those two countries.
Yeah.
I think again these are solvable problems. I don't think there's anything that prevents dramatic reductions in the cost of manufacturing these gyrotrons, which the number you quoted, by the way, I think that's a reasonable ballpark estimate for the cost of the entire system. So not just the gyrotron, but the magnet, the high voltage power supply that takes electricity from your grid or diesel generator and converts that electricity into the voltage and current we require for operating the gyrotron. We think, if we can create the demand, the pull for these
Yeah, the market
industries
will
to
follow then.
manufacture. Exactly.
Yeah. Did you guys make it all yourselves, or do you use partners?
We use partners in this
Yeah.
space for manufacturing of all the gyrotron components, and definitely have a strong say, I would say, in the design of those systems. But we are leveraging partners in the existing supply chain.
Something I didn't realize last time I spoke to you was any type of understanding for the economics behind your business, and also what the difficulties might be when it comes to raising money because of those economic risks that are faced. And so that's the framing for this question, which is there a traditional drilling method that is already in existence that could conceivably go 10 kilometers, 15 kilometers deep? Or, in other words, is Quaise's advantage not that its technology can do something which other existing technology can't, but rather it just promises significantly better economics at doing it?
It's a little of both. So, I mean, we've drilled worldwide, the industry's drilled wells to 10 kilometers vertical depth, but it's only two wells. There's technically there's the KTB borehole in Germany that was drilled to about 9 kilometers depth. The Kola borehole, most famously by the Soviet Union, was drilled to 12.5 kilometers
Just for
depth.
lols, yeah.
Yes. It actually relates to an inverse space race where,
Yeah.
similarly, our race to the moon, the US and the Soviet Union competed on who could drill deeper. And the US, on our side, we thought it wasn't necessarily worth the capital investment to go deeper, and the Soviet Union kept going at it.
Nice.
Kudos to them.
Yeah.
But the Chinese have also recently drilled a 10 kilometer, actually, I think almost 11 kilometer deep borehole in this very deep sedimentary basin they have in the western part of the country. The challenge is that those operations took a long time to drill to those depths. And as we said earlier, time is money. Kola
Mm.
borehole famously took about 20 years. This deep well that the Chinese have drilled quite successfully, it took them, I believe, in total 580 days. And I think the interesting data point from that deep well is about half that time was spent drilling to 10 kilometers depth. And the second half, or about close to 300 days, was spent drilling the final 900 meters. Kind of
Wow.
just
Yeah. Says a lot.
showing the challenges as you go deeper.
Yep.
It's not necessarily a linear increase in drilling challenge with depth. There's inflection
Mm.
points where it can get much more challenging to drill to those depths conventionally. And I think a final detail to note is it's not just about drilling deep, but drilling hot and deep. I
Hmm.
think if we're talking about our ultimate target temperatures and depths, which is getting to temperatures of 400 or 500 degrees Celsius at depths of 10 to 20 kilometers, where this super hot geothermal resource becomes ubiquitous, there's a handful of wells that have drilled to 10 kilometers depth. And there's a handful of geothermal wells that have drilled to 400, 500 degrees Celsius. But no one at this point in the game has drilled to 400 degrees Celsius at 10 kilometers. In fact, in those very deep drilling operations I mentioned, the Kola borehole most famously, they selected a site in the Earth's crust where the geothermal gradient was very low. So it was very
Mm.
cold rock they were drilling in because of the added challenge of trying to cool the temperatures at the bottom of that hole such that that conventional drilling equipment is able to operate at those depths and temperatures.
Do you have any sense for what China are doing with geothermal?
So I know that China is, I think, by far the world leader in shallower, lower temperature geothermal for the purposes of heating and cooling. I
Hmm.
think through a combination of the ground source heat pump approach to geothermal, which pedantically isn't technically geothermal energy, but gets bracketed under the same umbrella, as well as drilling into high temperatures for direct use heating. I think China is by far the world leader in that style of geothermal installations in terms of providing heating and cooling for residential areas and built
Mm.
commercial buildings and so on. We, you know, I wouldn't say I'm the most informed observer on what China's doing on the high temperature geothermal side, but I can only imagine that because they're pursuing, I think, an energy independent strategy and are considering pretty much all energy options on the
Hmm.
table, whether that's solar, wind, nuclear, coal. I have to imagine there's programs in that country that are dedicated to finding ways to exploit their high temperature geothermal resources. And I think in the past, a lot of that exploration has been in the Tibetan Plateau region, where surprisingly there's actually some naturally occurring geothermal resource that is present. If I had to speculate, I think we'll probably find there's a time where China announces they're starting to develop high temperature geothermal resources, and in a few months to a year's time, it'll probably come out that they're installing hundreds of megawatts, if not gigawatts, of
Yeah,
geothermal.
yeah,
Because that seems to be the trend with solar as well as nuclear coal. Their ability to deploy gigawatts of capacity on a
yeah,
month-to-month basis is quite impressive.
yeah. So Quaise hasn't gotten any inbound from some sort of consultancy firms that are Chinese based to help, learn, etc.
That's right. We haven't. I
But you
think long
guys,
ago, early at the founding of the company, we seen there was some interest from
mm,
some Chinese companies in the millimeter wave drilling technology, but
yeah.
nothing of recent to note.
Something you said last time was that the IP is more of a recipe rather than a patent. And so I just wonder what progress you've made in defending or licensing that IP. Because conceivably, if people see all the news from what happened over the last week, or at least what was announced yesterday, and even project 3, 4 years into the future, you actually prove here we drilled a 10-kilometer well with better unit economics than anyone else has, there will be a huge interest for that technology, right? So, how exposed are you to either theft or just copying, or how much control do you have over the technology?
So we hold an exclusive license to the original patent from MIT on the millimeter wave drilling method. And since the founding of the company, we've filed and gotten approved several patents that relate to key aspects of the millimeter wave drilling process that we think are important to protect. So that, I think more than anything, what we're most concerned with is guaranteeing we have freedom to operate as we continue maturing the drilling process. And there isn't going to be a party that says we hold a patent to this process, you're unable to do that. So patenting aspects like our waveguide design, how we are designing waveguide that is compatible in the drilling environment,
Hmm.
certainly a key aspect. How do we translate that waveguide into and out of the hole for drilling? Because that's a very novel function compared to what's done in fusion. There's no real need for moving waveguide parts for a nuclear fusion reactor, whereas for us, that's a key requirement for drilling. So that's sort of a example of the types of IP we want to protect with patents such that we guarantee that freedom to operate. But certainly then there's the aspect of the drilling recipe I mentioned, which is something we keep very much in-house, very similar to the Coca-Cola recipe, right? Coca-Cola does not have a patent on the recipe, but there's two people in the world that know the recipe and it's kept under lock and key.
Yep.
So that's certainly the drilling recipe is something we keep close to our heart here in the coming years.
So that's incredible. You could conceivably maintain your informational advantage even in a world where the whole world is looking at you and seeing what you're doing and potentially wants a part of it for themselves.
That's right. I think that the drilling recipe is pretty important to protect.
Yeah.
But more than that too, I think there's again, it's a lot, not just the drilling recipe and this balance of parameters that affect the drilling process, but there's a host of procedures, not the kind of things you would necessarily patent that are
Hmm.
critical
Know
to
how.
operating this,
Yeah.
right, exactly, know-how to operating this drilling rig in the field that I think, even if, per se through some espionage or in some means someone gets access to that recipe, I feel
Hmm.
confident we're going to protect our ability to execute millimeter wave drilling better performance than
Hmm.
potential competitors in the future. Because there's a lot of details, beyond um, the cool fancy stuff in the millimeter wave drilling IP
Yeah.
and how you make this work in a field operation.
Yeah.
They get overlooked, but are just as important.
You mentioned earlier that the gyrotron was 10x more powerful than it had been reported previously. I'm not sure what from when to when, but at least if you look at, say, the chip industry, where every 24 months, more transistors fit on the same size silicon wafer, and therefore the output of that same chip over time becomes significantly more powerful. Can you expect not the same rate of improvement, but the same principle would apply to the gyrotron technology, where you can conceivably continue to make 5-10% increases in its power over time with more innovation, more people working for you, more of that serendipitous discovery? Or
I
is
think
there like
there's
in the physics, is there a fixed limitation? We actually just cannot go stronger than this.
I think there is room for improvement in increasing the output power of the gyrotrons. For us, what's attractive about increasing output power is, again, not just increasing speed, but increasing the size of the hole that we're drilling. What we see right now is that the gyrotrons produced today that can produce up to a megawatt of output power. That output power is sufficient for drilling at least at minimum an 8-inch diameter borehole. But if we want to increase the size of the hole that we're drilling, which allows us to produce much more geothermal power from these reservoirs we want to
Hmm.
create, then there is an incentive for increasing beyond probably that megawatt power threshold. There's also good reason to increase the output power, which is attenuation down the waveguide. There's definitely going to be some loss of the microwave energy as it travels down this very long transmission line. Something we don't see yet as a real challenge in our
Hmm.
drilling, even down to 100 meters, but 10 kilometers, now we're talking 100 times the transmission distance. And so in theory, these waveguides show you can transmit this energy extremely efficiently, upwards of 90% over 10 kilometers distance. In practice, that's probably not going to be exactly the case, where there's going to be, say there can be imperfections in the waveguide design. We likely aren't going to have a perfectly straight path transmitting this microwave energy. And so we'll also need more power at the surface simply to overcome that attenuation down the waveguide. But I think to your original point on sort of the Moore's law analog, I don't know if necessarily there is a Moore's law as analog to how we continually increase the output power of the gyrotron, but we think it's plausible. And it's not just about increasing the power of one gyrotron, but what we see in nuclear fusion is that there's ways in which you can combine the beam power of multiple gyrotrons. And so
Hmm.
there's avenue to really increase the power we're delivering into the bottom of this hole for improving the size of the hole and the speed at which we're drilling.
And the size of the hole is its circumference, but the actual depth that you go for every blast doesn't change, or could the depth also increase?
I think the depth will continue to increase, but not necessarily the temperature that we're
Hmm.
targeting at that certain depth. There's diminishing returns to, it's better to go hotter, but past a certain point, there's going to be diminishing returns to continually going deeper versus the increased power output we can get from
Hmm.
producing geothermal fluid at those temperatures. And so there
Yep.
is a certain temperature horizon that we don't necessarily want to go deeper than. But the benefit, the incentive to go deeper is to really increase the scale at which we can access those temperatures. I think what we talked about maybe last time is that at 10 kilometers depth, there's broad areas, pretty much every state in the Western US, you can access these super hot temperatures at 10 kilometers depth. If you can double that to 20 kilometers, now you're talking most
The
of the
whole world.
continental US and more or less the world at large has access to these temperatures at those
Hmm.
depths.
So is your North Star metric always going to be what is the cost per, say, kilometer of drilling? That's the main thing you need to bring down.
That's right. Cost per meter. And I think it's not just like an absolute value, but it's a curve. Because what we see
Hmm.
in traditional drilling is that the cost per meter increases exponentially, or rather the cumulative cost of drilling increases exponentially because that cost per meter is increasing.
Yeah,
So for us,
like
we
that
want
example
to
you gave in China, where it took them 50% of the time to go 9% of the way.
That's right. For us, the goal is to flatten that into a linear curve. So this drilling cost of $1,000 to
Right.
$2,000 per meter stays the same whether you're at 3 kilometers or 13 kilometers depth.
So you're looking at the success of a company like Fervo, obviously Evers in the mix, and a lot of other ESG at shallower depths. Where do you see the strategic trade-off versus just sticking to your deep drilling roadmap? If you guys can all of a sudden come in and drill cheaper than Fervo and Ever, is there conceivably not like a business model that you can siphon off there as well to be more appealing to the investors and raise more money for yourselves? Or are you just focused? Deep is all we care about.
I think for us for us the real value is to go hotter and deeper. I think what Ever and especially what Fervo's achieved with EGS is tremendous achievement. I think they have a viable business in developing the geothermal resources that they're targeting, which is mostly in the Great Basin of the Western United States. But for us, if we want to realize geothermal at the terawatt scale,
Mm.
where we can develop geothermal in the eastern US or in countries where geothermal is an afterthought, we have to go deeper and hotter to justify the cost of going deeper. And that to me is where the real value proposition for us lies, is this ability not just to do, I think, a more economic geothermal in the same locations where those other companies are developing geothermal resources today. And the reason for that is just that by going to higher temperature, we're getting much more power out of these wells than at the lower
Hmm.
temperature. But by going deeper, we expand the scale at which you can develop that geothermal resource. And I think that's a very appealing point to investors and off-takers in the industry, wanting to procure geothermal power. I think unfortunately, we can't put all of our energy demand needs in the Western US. I think we need a means to develop geothermal in the places where it's not even in consideration at this current point, like the Eastern US, for example.
Hmm.
And in our view, the only way to realize that practically is to go hotter and deeper.
And should the technology be proven at scale, what are the applications beyond drilling holes that your technology might be able to contribute to?
Certainly. So focus is on deep geothermal drilling, but there is other drilling applications where this millimeter wave drilling technology can have value. Mining is an excellent example where you're drilling exploration holes or drilling these small drill and blast holes where they're coming back in and filling those holes with ANFO or some explosive that blasts out the rock to extract it for ore processing. Definitely, I think there's some value in millimeter wave drilling in that application since they are also drilling in more harder crystalline rock for those mining applications. Really, I think broadly there could be applications all over that involve hard rock destruction. So in any application where you're having to go through hard rock, which is challenging for mechanical drilling or boring technologies, I think there's an avenue for a millimeter wave type application. One other example that we explored quite a bit in the early stages of the company is tunnel boring. And certainly increased interest in not just boring tunnels for transportation infrastructure, but boring small tunnels for utilities such as electric power
Right.
lines that people
Yeah.
want underground. I think if there's areas where you have to do that boring in hard crystalline rock, that's an area where perhaps an application of millimeter wave to the rock allows you to bore through that rock more efficiently and without increased wear and tear on the mechanical tools that traditionally do that job. But definitely in the foreseeable future, our focus is going to be on the deep geothermal drilling
Yeah.
application for two simple reasons. One, we think that's where the value proposition of millimeter wave drilling is strongest in terms of the advantages it provides over conventional drilling. But secondly, it's just a much more massive market
Mm.
in terms of the impact it can have.
And it's also just way more exciting. You
That too.
know, like the promise of Quaise is the most compelling sort of business plan I can think of. Here's a technology that might conceivably enable energy dependence for many countries across the world, which sounds kind of ridiculous, like it's too high of a bar to even go for. But should you be able to drill to 20 kilometers at some type of decent unit economics, that's completely realizable.
That's right. Yeah, I mean, the way I see it, the closest analog in energy to what we're aiming to achieve with our deep, super hot geothermal approach is nuclear fusion. This ability to develop sort of right energy dependence and security virtually anywhere on Earth, utilizing the resources that are right underneath people's feet.
Yep,
I
we already
think to
have.
our advantage, not only do I believe the technical challenges are more solvable, but there is also an industry today, the oil and gas industry, that once they see, I think, the promise and returns implied by going to super hot geothermal, will be willing to jump, both feet in and actually scaling geothermal at the same scale at which they extract and produce hydrocarbons today for energy production. So
Mm.
I think there's, there's technical challenges, of course, and that's absolutely what we want to address through Quaise and with partners. But the promise is so high that
Yeah.
it's absolutely worth doing.
And it really is only technical challenges that you need to overcome. Is there any big legislative or political or supply chain kind of like you mentioned earlier, or are they all much smaller hurdles? It's really just the technical proving it out is the major challenge.
Yeah, I think it is the technical challenges that are by far the big barrier to enabling this right geothermal anywhere approach.
Hmm.
And it's not just pertaining to the drilling, but once you get down to your target temperature, you have to find a means to extract that heat in a wide swath of locations. And in our view, the best approach to doing that is taking a similar approach to what Fervo's doing today with EGS, going down, drilling wells, completing those wells at these temperatures, and then performing hydraulic fracturing operations to create a geothermal reservoir
Hmm.
independent of the naturally occurring geothermal reservoirs that we predominantly produce geothermal energy from today. So the technical challenges aren't just in the drilling, but also fall under the wellbore completion, the hydraulic fracturing operations, the production from these reservoirs, ensuring you can produce that energy sustainably over decades without depleting the heat too rapidly. There's definitely other technical challenges beyond the drilling, but to your point, we can, once we solve those technical challenges, I don't think there's any inherent physics limitations or economic limitations that prevent this energy resource from scaling rapidly.
And if you own the technology, would you just then be licensing it out to other people, or does Quaise become like 100,000 plus employee company where you have full ownership over all of the wells that you're drilling and owning?
Yeah, our aim is really to be a developer of super hot geothermal well fields. And
Hmm.
so, yeah, I would phrase it as we're a technology-enabled developer of super hot geothermal resources. We want to leverage the drilling technology to be able to go to places where geothermal is not being developed today, use the millimeter wave drilling to get to our target temperatures, and then execute the development of a geothermal well field and with partners construction of a power plant such that we can produce useful energy from this super hot geothermal resource. That plan will evolve, not just with time but also probably with where we are in the world. And ultimately I think at the beginning, like many developers, you have to get in the business of building your own power plant. But I think where the true value lies in Quaise is everything that's in the subsurface. It has to
Hmm.
do with the drilling. It has to do with the stimulation, reservoir creation, and production from that well field and reservoir. And in an ideal scenario, we're working with partners that operate the power plant and a lot of the surface operations. And we're involved tangentially to some degree in ensuring the well field is operating to performance. But the benefit of that approach being that we can focus on rapidly scaling these super hot geothermal well fields, almost in an analogy to how oil major like an Exxon develops an oil and gas well field and produces that oil and sends it off to
Right, right, right.
refineries and the end use consumption
So,
further downstream.
so that kind of means you would maintain as much as possible the whole means of production through to it finally being sold off into the grid.
That's right. And I think,
So that means Quaise has hundreds of thousands of employees if it proves out.
just yeah, I think to a certain
Right?
point we
That's
need to
kind of crazy.
rapidly, right,
Yeah,
scale the footprint of the company.
yeah.
Definitely, I think long term, maybe it proves out that a more technology based licensing model proves value, but we need to have the partners that are willing to execute those projects. And so for us, I think we made the decision about a year and a half, 2 years ago to say that, we need to give a landing spot for the millimeter wave drilling. There's no company developing super hot EGS projects today. And for that reason, we need to become that company to pair with the drilling to realize the true promise of what we're doing at Quaise.
Is it too early for Quaise to be thinking about the commercial partnerships that you might conceivably have? Like if you look over to my corner of the world, there's Indonesia and the Philippines and Japan, some of the geothermal leaders internationally. Like, are you developing relationships with people over here to become available once the technology is proven out, or is this all just like once the technology is done, that'll all take care of itself?
I think those discussions are already in progress. I think right now we're focused on developing our first project here in the US, and really our um, commercial relationships we're advancing are with the partners that help us execute that project. Can include anywhere from contractors that are installing the cement to helping us with the hydraulic fracturing operations, building out the roads, surface infrastructure we need for the well field and power plant. Um, but as well, on the commercial side, talking with off-takers that are going to be the first off-takers for the energy we're going to be
Yep,
producing.
yep.
We've definitely been in advanced discussions in finding the right off-taker for this first geothermal project we want to develop in the next 5 years here.
And an off taker would be an energy company that are
Yeah, I
charging
mean, I think
directly to consumers?
all over, I think utilities, industrials, certainly the AI hyperscalers are probably the biggest source of
Oh
increasing
yeah, of
demand
course.
here in
Yeah.
the foreseeable future. So
Dig a well
we're
next to a data center.
that's right. And again, promise of super hot geothermal being able to go to a variety of locations. You can drill the wells right where you want to do the data center in the long term.
And so that's sort of moving away from the original idea, which was repurposing old coal power plants.
That's right. I think there's still some interest there in the long term.
Hmm.
The real value in, I think, repowering the power plants isn't necessarily to take advantage of the existing turbine generator infrastructure that's in the power plant. I think something we've found as we've dug into that concept more in depth is that it can be challenging to produce geofluid at the surface that perfectly matches the inlet conditions of the turbine generators that are already in that power plant. But going to an existing power plant provides several advantages to a greenfield project once we're at a stage where we can develop these super hot geothermal projects more or less independent of location. That includes having an existing interconnection with the grid. That includes having existing rights to using the water that we need, not just for creating the reservoir,
Right,
but also
right.
the water we need to be cycling through the reservoir long term. And so it's definitely on the long-term roadmap for commercial development. But I think in the foreseeable future here, we're more focused on the greenfield opportunity simply in that it gives us more freedom for choosing the ideal location to develop our first project, where we don't
Hmm.
necessarily want to go to 20 kilometers on that first of a kind geothermal project. But by going to a site where we can access this heat relatively shallow, and in fact could even access that heat with conventional drilling just at a higher cost, it's the most risk-averse approach, I think, to developing the first commercial project, and then in subsequent projects begin to extend the depth at which we're drilling to and producing geothermal energy from to expand the scale and footprint of where we can do these super hot
Hmm.
geothermal projects.
When you and the team, or yourself and Carlos, or you guys get together and you've had a couple of drinks and everyone's in a really good mood, what's the vibe about? What are people most excited about with the work that they're doing? What are the big visions of the future that they start painting in the discussion between each other?
I think all over the place. I mean, definitely on the drilling side, ways in which we can continue to, just yeah, along with the traditional roadmap, like the ideas we have for how we ensure to continue drilling deeper, address some of these technical challenges I mentioned, such as, preventing borehole collapse. I think on as we've gotten more into the project development game, there's a lot of excitement just for in how at the scale at which we can develop projects, given that we have this increased power output from our wells, this decreased land footprint, this ability, it's something I think we get excited about is as we start to develop a commercial project, you start, in a phased approach where initially you develop a well field and power plant that's producing X amount of megawatts. But I think because we have this decreased footprint, we can almost imagine we can develop these gigawatt bundles
Mm.
of geothermal well fields and power plants that is really the scale that we need to be talking about with geothermal deployment, because the rate at which we need to install energy in this day and age, not just for a decarbonization goal, but again to meet this rising demand from AI, we need to
Totally.
develop these gigawatt scale energy projects. And I think that's the
Yeah.
exciting thing about going to higher temperatures. That actually looks very feasible, just given you can get upwards of 30 megawatts per well by going to these higher temperatures.
I heard this today on The Rest is Politics, not by Rory Stewart, but by the other co host. And so if this stat is wrong, it's on him. But in Ireland, forget the number, but they've installed a huge number of data centers. Ireland is kind of like a European headquarters for so many of the large American software companies for tax purposes. But nonetheless, the big point that he was making here, which as much as 20% of Ireland's electricity needs are being diverted to these number of data centers, which now I'm saying it almost sounds ridiculous, but I'm certain that is actually the number that he gave, which is absolutely wild. If we're thinking about the ubiquitousness of these LLMs being across all of our softwares, all of our consumer softwares, business softwares, the the enormous compute requirements and the electricity to farm these data centers is going to require, we might be doubling, tripling, quadrupling our actual energy requirements just for electricity in the foreseeable 10 years, 15 years.
You look at the scale at which these companies are wanting to install data centers, and it's pretty stupendous. I think there was a recent announcement in OpenAI, they're looking to build 3 to 5 gigawatt data centers. I mean, these are data centers using energy on the order of large cities, millions of people, simply to power one of these models for training. And I think there's only reason to believe it's going to continue to grow. I know I've heard arguments that, what happens if they are able to make the computation more efficient, which I think is a good thing, that it uses less energy, but there's a paradox there that's noted with energy efficiency, where when you make things more efficient, it doesn't necessarily mean you reduce the energy use. It just means you increase the penetration or the ability to use those things at greater scale now that it uses less energy. So I think, there's only room, continued room for increased demand from this AI application that really, really is requiring reliable 24/7 power, as well as a lot of these companies having clean commitments as part of their energy procurement. They want to procure clean, firm power. And so I think, super hot geothermal is really just the perfect solution there in getting the power they need independent of location. As we mentioned earlier, you can co-locate these well fields and power plants with data centers in the future to minimize that transmission cost, or even if they want the ability to rapidly spin out a data center the way that some of these companies do today with natural gas turbines. We think we have the ability to do that in the long term with super hot geothermal. And I think it's been a major reason we decided to push into developing geothermal projects while we're still advancing the millimeter wave drilling technology, because it was very clear that this is a pretty spectacular moment for geothermal, in that all the stars are kind of aligning to really demand increased growth from the industry in the geothermal energy sector. And we're hoping to be a key party in helping enable that.
What about the politics? Is that on Carlos's shoulders, your shoulders, your business development shoulders? How do you interface with whatever the situation looks like with your government and trying to get state funding, national funding, etc.?
I think a bit of all of us, to our benefit. Energy has obviously been a bit of a political football in the U.S. between both sides of the aisle, and I think favorably, geothermal has remained a bipartisan energy source. One side of the aisle sees this as a source of clean energy. The other side sees drilling. They see an industry or potential market for the oil and gas industry to jump into. And they also see, I think what both sides see is the argument of energy security and energy independence, the ability to develop these energy resources in the US and potentially in any country where there's going to be heat if you go deep enough.
Look, I've just got three more for you. Hopefully, one of them or two of them is fun, but we'll be able to wrap this up shortly. So, you've once said, in fact, I think it was last time we spoke, the one advantage is the geographically agnostic deployment. And so, I wanted to ask you, forget what's reasonable or what makes most sense, just where your heart is. What is the first country, first site you want to go to, should you be able to drill 20 kilometers deep reliably?
Whew, yeah, that's a good one. I mean, showing my national bias, I'm very excited about going to the eastern US. I think it's just geothermal is an afterthought out here, but if you look at the US, most of the people are east of the Mississippi. Most of the energy resources are west of the Mississippi. There's not really a domestic energy source east of the Mississippi that can help power all the energy needs we have out here, like where I live right now in Massachusetts. And so when we talk about geothermal in this state, um, people think you're talking about residential heating, ground source heat pumps you install in your home. No one's thinking about geothermal power plants producing energy. And so I think I'm definitely very excited, specifically within the US, of getting geothermal out into the eastern US, which I think once we develop a project of that magnitude, it really sets what our value is in this company, that we aren't just developing geothermal in the places it's widely developed today. It's actually being developed, it's demonstrating that value of this geographic agnosticism.
Yeah. Wouldn't it be incredible if Quaise technology enabled some of the gigawatt hours of Manhattan on any given day?
That's right. That's where we want to go.
What's the role that serendipity's played within Quaise so far? So you're experiencing many technological improvements over time, but I just would like to touch on whether anything particularly serendipitous has stood out.
Interesting. Yeah, I mean, I feel there's a lot to choose from. I think definitely early on in the founding of the company, serendipity played a pretty big role in bringing myself and Carlos together, meeting with Paul Waskoff. Um, I can remember definitely just, this is a personal bias for me, but I can remember being in grad school. I had just started learning a bit more about geothermal energy through a class I was taking and was exploring, opportunities to start, a career in the geothermal sector. This is way before Quaise even. And I was talking with a really good friend of mine about it and expressing some concern about, oh, I don't know, this was I would say kind of a low point in where geothermal was in terms of optimism for the industry about 8 years ago or so. Wasn't, view was most of the geothermals tapped out in the US. Technological innovations, aren't really going to get us there. Wind and solar aren't necessarily, we aren't going to be able to compete with wind and solar on a LCOE basis. And I, kind of expressed those concerns to my friend. I'm like, yeah, I don't know, is this really going to be a industry? And he kind of, remotivated me to think, like, no, you like are clearly very passionate about geothermal energy. And so my friend, really motivated me to think about, that this is actually an opportunity to uh, do something, that there's actually tremendous white space in geothermal to think about new ways of producing geothermal energy in a way that changes that paradigm. I would say another serendipitous moment for me was working in the geothermal industry for a brief period as an intern. We would drive out to these geothermal projects in central Nevada, and I would always drive by a 500 megawatt gas plant and think that that gas plant is producing more energy than all of the geothermal projects we're developing here in the Western US, owing largely part, I think, to the fact that these are lower temperature geothermal resources that just simply don't compete with hydrocarbons on a energy density basis. And that got me really interested later on when discovering some of the work that the Icelandics and the Japanese and the New Zealanders had done on increasing the temperature to super hot temperatures and looking at trying to produce energy densities much higher from geothermal energy by going higher temperature. So that was a moment early on that I think clicked for me for seeing that, maybe there is, by going hotter, you can really change this picture people have of geothermal energy to being a niche thing, going to places, like in Iceland where you're getting, very hot water coming out, to what if there's a way to do geothermal that looks a lot more like oil and gas development in terms of the energy output you're getting per well, in terms of the economics, and if you can find a way to go deeper, a way to produce geothermal at the same scale that oil and gas is produced at.
And that 500 megawatt gas plant that you drove by, let's make just a direct equivalent to should you hit 15 kilometers of depth in any given part around the world where it's decent for rock temperature. What amount of power would this turbine, therefore attached to your Quaise well, be generating?
It would all depend on the number of wells. I think what we're modeling right now, and had one of our colleagues present his work at the Stanford Geothermal Workshop and some other conferences, is that 3 wells can get you upwards of 30 megawatts per well triplet. And there's room to improve that upwards of even 40, 50 megawatts by finding ways to drill larger holes from which we can produce that power. So certainly, I think you can get upwards of a gigawatt probably through several power plants rather than just having one central power plant producing all of that energy. But it's really just a calculation of how many wells you want to drill to meet that prospective demand of 500 megawatts. In the example I just gave, we're talking, I think on the order of um, 40 to 50 wells.
Okay, great. I just wanted to get a, like a sense for how much power are we really talking about here. But finally, Matt, what happens now? So you had the big announcement yesterday. We've just discussed quite a little bit about the technology, some of the business model, the limitations, the exciting things as well. But what happens now?
What happens now, I'd say there's two prongs to focus on. One is the drilling development, the second is the project development. So on the drilling technology, we're going to be continuing testing at our same site, and over the next year, 10x that depth milestone from drilling 100 meters to a kilometer in depth. It's a pretty major milestone for us because something we heard very early on from people in the oil and gas industry is that we will take a seriously look at this technology if you can show a kilometer hole in the ground. And so that's something we really want to focus on proving out in the next year with the same system and the same site in Central Texas where we're drilling. We also want to commission our first full-scale millimeter wave drilling rig. This is going to be integrating a megawatt-sized gyrotron system onto an existing onshore drilling rig owned by Neighbors Industries, who's a partner investor in Quaise. That's a system that would be ready to mobilize for the first true geothermal drilling trials. And our roadmap is that first commercial drilling campaign takes place sometime after the kilometer milestone in 2027, 2028. That's going to be drilling a 3 to 5 kilometer deep hole into 400, 500 degrees C temperatures in the rock. So that's our roadmap on the drilling side. On the project side, we've secured several leases in the western U.S. in Oregon, Utah, New Mexico, and we're right now winnowing that down into the final site to develop our first project. These sites all have favorable attributes in that we can access these high temperatures relatively shallow into the subsurface. Once we finalize that site, as well as secure a commercial agreement from our prospective off-taker for developing a well-fielded power plant at that site, we're planning to execute some exploration activities to narrow down some of the key geologic parameters we want to understand, not just for drilling, but also for reservoir creation. So temperature at depth is going to be a major quantity we want to nail down, but also the geomechanical properties in the rock that inform how fractures behave for designing an EGS reservoir. Those are key parameters we want to extract most likely from an exploration well we drill at the site. In the next year, once we've raised our next round of financing in Series B, we want to finance that millimeter wave drilling roadmap I described earlier, but we want to also put that money in starting to develop this first geothermal project. And the way we would do that is actually starting with conventional drilling. Because as I mentioned earlier, at these sites where the heat is relatively shallow in the subsurface, we've shown, the industry has shown you can drill geothermal wells into those conditions. I think millimeter wave drilling will be cheaper in that same environment, but in the near term, we can use conventional drilling to get the project started and drill our initial wells, connect those wells through hydraulic fractures, and demonstrate through a flow test the potential for producing energy from those wells that matches what we've modeled, such that we can move both the drilling and the project in parallel. And in 2027, 2028, those paths will intersect. We'll have matured millimeter wave drilling to the point that we can then expand the well field through millimeter wave drilling and start building the power plant that is producing the initial power from these initial set of wells to meet the demand required by our off-taker.
And should that power plant work, then it's game on. It's proven. So
Game
now it's
on.
just about
Yeah,
scale. Amazing.
it's about scale.
Sorry, that was meant to be the final question, but it was something that I forgot to ask you earlier. You mentioned that you're going to be raising more money as a Series B. To date, you've raised something like $90 million.
That's right. I think 95 million, as well as being a member to a 5 million grant from the Department of Energy.
And what are you looking for now?
Yeah, I think we're looking for on the order of 200 million. I
Right.
think that's what's needed to both start the project development and advance the drilling technology from this 100-meter milestone to a deep geothermal borehole
Yeah.
in the ground by 2028.
And is that coming from venture capitalists?
I think a bit of both. Definitely venture capital would be involved. I think this is a stage, especially with developing a project, that you maybe look beyond those venture capital sources that are very focused on technologies, looking at investors in infrastructure, corporate strategics, family offices who I think have gotten a lot more invested recently in some of these tough tech startups that require a lot more money than your more traditional software startup that's been the typical name of the game for venture capital. So a little bit of all of the above, but definitely venture capital is still a big source of funding in the near term.
Cool. Look, Matt, so generous with your time. Thank you so much for speaking with me again today. And I'm super keen, obviously. I think I'm your biggest fan over here in Australia. So I'm keeping an eye on
Thank you.
everything.
No, I appreciate it. Looking forward, 10 years down the line, maybe we'll get our first project in Australia going.
Yeah,
I'd
mate.
love to have an excuse to go visit.
All right, mate.